Good morning and welcome to our discussion on exponential and logarithmic functions. So where are we? We have looked at the natural logarithmic function and we expanded that to the general base logarithmic function, but regardless of which base you look at, we had some properties. Now, if you remember one of the properties, I'll just write it for the natural log function, since that's what we mainly need it for. If I have the natural log of something to the power of something, and those two, a and b, could be very complicated or just numbers. Then, interestingly enough, I have that equivalent to the natural log b, the exponent that was inside the log previously, times the natural log of just a. And we did some examples and said that most of the time it's a quality of life thing that can make my life easier if I simplify first, like this, if there's an opportunity, and then go and look at a simpler log expression. However, I can also use this to handle general exponential equations. Now, previously, we have seen the basic exponential equation where I need the bases to be the same. Using this property in logs, I don't need that anymore. For example, now we're not going to do a ton of these. I really just want to draw your attention to the fact that we can handle all kinds of equations now by using the log function and that specific property. And it'll come up now and then, but we're not going to give you a whole bunch of these to do just for the sake of them. So now I see clearly, right? The bases are not the same, and I can't make them the same in any way. A key property of the logarithmic function, similar to the exponential function, is that if, what should we call it? I don't even care. I don't want to use an a and a b again, but I will. Maybe not. What should I call it? If f of x is equal to g of x, now those could be numbers as well, then that's equivalent to the log of f of x equal to the log of g of x. And it goes to a property of the function. Function is called one-to-one, and one-to-one functions have these properties. Maybe you know something about that, maybe you don't, doesn't matter. It's similar to the exponential function. So we casually say, oh, we take the logs on both sides, but that's okay. So what I'm going to do is exactly that. I have a left-hand side equal to a right-hand side. It doesn't matter what they are. Then the log of the left-hand side is necessarily going to equal the log of the right-hand side as well. Of course, assuming the function is defined there, and because these are exponential expressions, they're all positive, so everything's good. Now, for each of these sides, I'm going to use the power moving property, or whatever you want to call it. And because I have something to the power of something else inside the log. So that becomes, for the left one, 2x times log of 3. Remember, there are brackets there. I just don't write the brackets when there is one term. But you're welcome to. For the other one, I have something to the power of something else inside the log. So it's the exponent moving to the front, and just the rest is left. Now, notice that the log of 3 is just a number. Log of 4 is just a number. Your calculator has this built in. Actually, I didn't actually look to prepare what the log function is in MathBot. Let me just try. Let's just say log of 2. See what happens. It's not ideal. That's base 10. Okay. Let's try natural log, ln. Okay, perfect. So even MathBot has this ln function built in. So if I give it just a number, it's going to give me another number. I don't know what the number is. It's the y value on the function. Regardless, I can calculate these numbers. So this is one number. This is one number. People tend to separate the ln from the rest. No, it's not an individual thing. This is the representation of a number. Okay, so I have to solve for x. So if you want, you can say 2 times log 3 times x, a number times x. And this is a number I'm going to multiply in. The number is represented by ln 4 because it's an ugly, non-repeating, non-terminating decimal number. So I don't want to round it in the equation. I want its exact representation. So I multiply it in, and then I multiply it into the 1. And I like brackets here to remind myself this is one thing. Treat it as any other number. So now I can take the x's to the left maybe, and I'll have this when I factor out the x. And woohoo, that's an ugly ln. My apologies. That number stays on the right. Then all I have to do, notice I don't calculate this and then round the number because I could lose accuracy if I round anything other than my final answer. Don't want to do that. So it's a little clumsy to write this, but hey, it is what it is. So let's calculate that just to show you it's just a number. I just don't want to use a rounded decimal early. I could lose accuracy in my final answer. So let's see. ln 4 divided by, I have some brackets there, of course, 2 times ln of 3 minus ln of 4. Hopefully that is correct. And of course, in the meantime, you would have done that and you can confirm my answer as 1.7095. Final answer, I can round that. And I like 4 decimal places if nothing else is instructed for me to do. So with this quote-unquote taking logs on both sides property, I can handle exponential equations with different bases. It doesn't actually matter now. I'm good with anything now. But in the beginning, I couldn't do that without knowing something about logs. I need that property, which doesn't work with anything other than logs. Only they have this interesting exponent moving property, which is super weird when you really think about it. So a little bit of a side note, it can come up now and then, but not super often. So we'll put a pin in that. Just be aware that I can handle exponential functions if they ever happen to cross my path. So let's have a big picture of what's happening here. Again, I started with the general exponential function. Some base a to the power of x. I still don't know the derivative. Okay, that's fine. Then we moved on to, we made it a little bit more specific. And I like doing this kind of flow chart many times to remind myself, what are we doing here? Well, I changed the base and look at a specific base, E, 2.71828.1828459.045.23536, and then so on. It never stops. I enjoy trying to memorize some digits. For that, the derivative was the simplest thing I could possibly hope for, in that it's the function itself. Can't be much better than that. But it has to be that base. Okay, fine. Then we looked at inverse functions, and we found another function related to this guy. and we call it the natural log function. We gave it a name because it didn't have a name. Everyone should have a name. And for reasons we will eventually see, its derivative is also quite simple. It's not exactly the same function, actually not at all, but it's simple enough to remember. Okay, great. Then we saw that, well, okay, I should be able to go back and change the base for this natural log function as well, shouldn't I? And then we define, or we just name it appropriately to keep track of what the base is. And of course, I don't know this derivative at all. Okay. So we have some things left, but not too much, not too much. I just want to be aware of the relationship between the general exponential and log functions before we go for that derivative. Now, of course, we can sit and do examples, so many examples for the natural side. I don't really feel that we've done enough, but for the sake of time, I leave it to you. Do some problem book questions or textbook questions with answers and everything. If you want me to check an answer, just email it. It's all good, but you do need enough practice. So, just going back to the relationship between the exponential side of things versus the logarithmic side of things. I did the same thing for the natural case. I'm not sure if I wrote it down for the general case. It's worth doing again anyway. So I'm going to pick a base A. It doesn't matter. We pick a base. It's done for both. It's not going to change. The changing thing in the exponential calculation is you give me a number, b. I would then raise a to that number. Actually, I'm going to just change this to a specific number because it helps people perhaps, and then we'll change it. I did do this, but let's take a 2. I would take 2 to that power. You give me the b. So b is the input in the exponential calculation. I then get an answer c. And of course the answer depends on what b is, right? Input, output. The log side of things, they're doing the same thing. They're expressing the same relationship between 2, b, and c, just from the other side. That one says, I want to work with base 2. Fine. You give me the answer. You secretly do an exponential calculation and give me the answer. What the log function is doing is it will return the power that I have to raise to 2 to get that c. So on the exponential side, I'm given the exponent, I find the answer to the exponent calculation. On the log side, I'm working backwards. I'm given the answer and it returns the power of 2. Okay, so there are two unknowns. I can go one direction or the other direction. There are two sides to this relationship between b and c, given a base, of course. Now, if I take this and just say base a and not restrict myself to a specific example, of course nothing changes. I just have to not see the a in the same way as b and c. It's not. A is not something that you have flexibility on. You pick it, it's known, it's done, kind of. So a is the base. You give me a b, I raise a to that power, I get an answer c. The log side is the reverse. It says, give me the answer, and I'll tell you what the power of a should be to get you there. Okay? Very handy to be able to talk through it like this. I find it extremely helpful. Every now and then, every time people think, nah, I'm not going to do that. What does he know? Pfft, I'll just memorize what I need to. And then every now and then, this way of understanding the relationship makes things super easy. Understanding always beats memorization. So I can now rephrase some of those initial properties by understanding this relationship, or just by memorizing and looking at it as inverse functions, of course. I can't remember which one I did first. I'll just do this one. If I have an a and I raise it to the power of log base a of c, what am I going to get? I'm going to get c again, because they're inverse functions. Or you can say, well, this log represents the exponent for a that would give me c. I then raise a to that power, so I should get c. It's really quite simple. And the other one, log base a of a to the b, is just b. Because inside the log, I have a number, an exponential calculation. What is the power of a that would get me a to the b? Obviously b, right? If you understand how these things are related, these are trivial. Okay. Now, let's put a pin in this because we're going to need this guy. We're going to need this guy when we are up here in the general exponential function. But let's finish the general log function. So we have some properties. We still have the product property and the quotient property. We have this exponent moving property. There's one other property that's going to make the general base log function quite straightforward. Okay, last property. So if you look back, there are 6 of them, 6 properties, with different degrees of importance. Some are crucial, some are optional. Here's the other property, the last one. I'll give it a name actually, because it has a name. It's the change of base property. Now, you prove it in the same way as I did some of the others, but I'm only going to pick a specific case because it's the only one I'll ever need. So it says, if I have a base log function, let's say c, right? C is my input for the log side of things. This, and again, these are not intuitive at all. This property says, it turns out that I can rewrite this log function to a log function of a base that I can choose. I'm going to choose the natural one because I know everything about it. The downside is I'm going to have a fraction with 2 logs of that other base that I choose. I'm choosing the natural one. Then the input for the top log is the original input, c. The input for the bottom log is the base of the original log. Again, you can't look at this, well, I can't. You can't look at this and say, well, how am I supposed to understand how that could be? No, you have to prove it. You prove it in a similar way as we've done the others. If you want to see it, I can totally show you on the side one day in a Q&A session, whatever. It's not important to be able to prove it, but we need this property. This is crucial to find the derivative. Now, let's take our general base log function. Let's take 2. Let's just make an example here. I find 2 to be surprisingly easier to look at than a, though there's no difference. So now what I'm going to do is I'm going to say, well, I don't know the derivative. I don't know what to do here. I'm going to rewrite this to a base e, to the natural log. Then the top one is still the original input, and the bottom one has the 2 as input, not base anymore. The base is e now. But notice what this is. The log of 2 is just a number. So what I have here is some number, let's calculate it, times natural log of x. Let's calculate it. 1 over ln of 2 come on, MathBot, 1.44. Yes, it continues forever, which is why I don't write the decimal number. I leave it in its exact form. But If there's no x, what I'm working with is a number, which means if I want to find the derivative of this, it's the constant times a function property. It's this constant in front of the function, which is the natural log function, which I know what the derivative is. It's 1 over x, and I'm done. So it's really quite simple, but I needed this change of base property. So then in general, if my function is any base, a of x, not necessarily a 2, I personally don't memorize this. I am just going to write the function with my change of base formula, realizing that it's just a number in the bottom. There's no quotient rule needed or anything here. It's constant times a function property. So the derivative is keeping that constant in front, derivative of the essence of the function, which is the natural log. So interestingly enough, and this is not obvious to me really, any log function is just a scaled version of the natural log, because it's just a constant times it in front, which I know transformation-wise is a vertical stretch or compression. So it's just a scaling of the natural log function, which means that technically there is only one log function that I care about, and it's the natural log, because as soon as I see any other log function, I just rewrite it to the natural log and work with that. There's only one function, which is why I just call it the log of x. There's only one. I see a log function with a different base. I don't care. Rewrite it, work with that function, because that function is much more straightforward. So now you can memorize this as a formula. I choose not to because it has no benefit to me, but we can certainly now complete the general log box. 1 over natural log of a, 1 over x. Easy, if I know how to do it. I don't choose to memorize this because this line of rewriting the base is super easy. Super easy. There's no memorization needed. I don't want to memorize stuff that I don't really need to memorize. There are times, sure. But if I can just get there with a one-line understanding, I'm just going to do that. So we're going a little fast, I feel, time-wise. I was worried that I'm not going to squeeze everything in. But let's just take some examples and just make sure of this situation. Let's pick something. Where are my examples? My examples aren't very exciting, I'm sorry. Let's take an example. Let's call it f of x, log base 3, x squared minus 1. I do look at it, and now I see a couple of things. Well, I'm looking for a couple of things. I'm looking for the base. What is the base? It's not e, therefore I'm going to change it, period. And I'm also looking at what is inside this log function. Is it something that I may want to simplify and make my derivative life easier? Can I even do it? I have to look. So I do see it's x squared, but there's a difference of two things, and I don't have a property for that. I have a property for a product or a quotient or something to the power of something else. Multiple terms, there is nothing you can do. Okay, but I do check, have a look, think about it. It's important because it's a quality of life check. So in this case, I see that I'm at the very least going to rewrite this to the natural log. Now, yes, it's like this, but I don't see, it's a quotient, but I don't see it as a quotient. Don't think that in any way this is a quotient rule necessity. You can do the quotient rule on this, but because one of them doesn't have an x in it, it's going to be completely a waste of your time. So then the derivative is simply going to be keeping this constant in front. And now I have a chain rule, right? The essence of the function is still chain rule required. Why did I say that so weird? It requires a chain rule, but it's a natural log, so that's not bad, of something. So the chain rule says, take the derivative of the outside function, natural log of something with respect to the something is 1 over the something. Times, says the chain rule, the derivative of the inside something, which is also straightforward. So if you want, put brackets there. Do not get confused what goes together and where and whatever. If you want to now put them up all together in one fraction, go ahead. But I like to leave it like this because it shows me and anyone who's grading it or anything else, it shows how I constructed the derivative systematically, which is important. People, to be perfectly honest with you, from an instructor point of view, people that just merge it into a single fraction and simplify it immediately, not even showing the detail line, they just skip this line and rush right to a simplified one. It's very difficult to grade and assess if you've constructed it accurately in some cases. When you show the detail, stretch it out, break it up into pieces, it's so much easier to verify that you know what you're doing and where mistakes may have occurred. So much easier. All right, I have one more example here, this one. I try and not make bases that are overly complicated, though you can. I'm just going to say, as a side note for us, actually not for us, as a side note, if you see somewhere in a book, just something like that, most of the time it implies that it's base 10. You get very old books that didn't use ln, but just use this log as the natural log. So just be careful when you see a log without a base. These days it means base 10, but really the base should be there. I think in some stats situations they use base 10 so much that they stop writing down the 10 because that's all they're going to ever use. But that's not what we want to do. So just be careful of situations like that could be read incorrectly. I will pick a base. Let's pick base 2. And I'm going to pick, oops, not that one. I don't want to pick just x. I want to pick the square root of our friend x squared plus 1. Now, I look at this and I see, okay, it's not base E. I want to change it. And I also see, there's a square root here, which I can see as the log of x squared plus 1 to the 1/2. It's not necessary, but it's going to make my life much easier if I now say this is 1/2 log of x squared plus 1. Because now I have a simpler function as my inside function. So it's much easier to work with. You didn't have to do this. You could have done it with the original one. Regardless, you need to change the base, regardless. So you either change the base here to 1 over natural log 2, natural log root x squared plus 1, or you change it here, the 1/2 is in front, whoopsie, change the base 1 over natural log 2, 1 over natural, no. Sorry, I'm all thinking about something else at the same time, which is never a good idea, x squared plus 1, of course. And then you choose. I didn't have to use the exponent moving property, but I did have to change the base regardless. Which one do you like? I like this one. I don't care how many constants are kept in front. I'm going to go ahead with that. So now the derivative, let's see if we can do it in one go. The constants just stay in front. There's a half that stays in front. There's a 1 over log 2 that stay in front. I don't care. They came from different places. That doesn't matter to me. Constant times a function property. Now I can focus on the essence of the function. And if I can make that essence as simple as possible, my life is going to be easier. So why not do that? Natural log of something, first part of the chain rule says, is the derivative of the outside function with respect to that something, which I know is 1 over x squared plus 1 over the something, times, says the chain rule, the derivative of the inside something, 2x. Put it together after the detail if you want to simplify it. I don't want to. Let's go to our last piece of the puzzle. Where's my big picture? Okay. All right. Last piece of the puzzle is this guy over here. What is the derivative of the general exponential function? Okay. Now for this one, let's see it first. Now, or lastly, or whatever word you want to use. Let's say f of x, whoopsie, is 2 to the x. Let's make it specific. It helps some people. And then we'll change it to an a and see nothing's not going to change. What's the derivative? Well, similar to the situation for the general log function, I don't know what to do. I want to refer back to the natural version. But in this case, there's no property to quickly rewrite this to the natural base. But there is one that I'm looking for. I don't know where I put it. Oh, it's up here. It's this first one. This says that anything, this C can be literally anything. I'm going to just use this property backwards. This C can be anything. And on its own, it's equivalent to some number to the power of log base that same number of that C. So whatever I want, you can call it C, you can call it whatever, is going to be equivalent to any base. I'm going to use E to the power of the log of the same base, and then that same thing that I started with. Okay. It doesn't matter what is in this square. C was never specified in this property. This is what I'm going to use. Now this is in the square. Doesn't matter what it looks like. Don't look at it. E to the natural log of that same thing is always going to be true. Now I'll just remove this square because I want to see. Oh, I don't have a lot of space there. Maybe I'll make a big square like that. What was that? It was 2 to the x. It didn't matter what it was. This is true always. Anything can be in that square. Well, anything positive. But now look at what I have. Let me remove that square. Look at what I have for that log. I have something to the power of something else. I have 2 to the power of x. So if I just focus on the natural log of 2 to the x, I can rewrite that. I'm going to do it at the bottom. I'm going to do it like this. I can rewrite that to x times natural log of 2. It's the exponent moving property of logs. Then I realize, well, this log of 2 is just a number. I'm going to help myself by just putting it in front and remembering, what is it? Let's find out. Let's calculate it. I think I have already, but let's do it anyway. It is just a number. It's 0.6931 and so on and so on. Just a number. So that means that instead, I'm going to see my function as a natural exponential function of some number times x. But some number isn't going to bother me in finding the derivative because it's just going to be the constant times a function property. So the derivative is then going to be the derivative of this, which is a chain rule situation. Let's make it super clear. I don't want any confusion. Let's write out the chain rule. Let's call it U. When things are a little bit uncomfortable for me, I always have that to fall back on. Then f is going to be e to the u, right? So this then says the derivative of f is going to be the derivative of f with respect to u, derivative of u with respect to x. Even though I don't write this every time anymore, it doesn't mean I can't. And when things are a little weird, I always have that safety net. Derivative of f with respect to u. It's e to the u. It's a natural exponential function. Derivative of u with respect to x. See it for what it is. It's a number times x. So it's the number. Now what do I do usually? I replace u with what it actually is. So it's log of 2, sorry, e to the power of that, right? E to the power of log of 2 times x, and then times in the base level log of 2. But now have a look here. Let's use some color. Have a look at this. This guy is exactly the same as this guy up here, which was the same as this guy, which was the same as this guy, which was the same as this guy. They're all equivalent. So by going backwards in the line that I started with, this in the pink box is the same as 2 to the x. I know it's a thing, 2 to the x. And then I have my log 2, of course, right? So, derivative of 2 to the x is 2 to the x, natural log of 2. Now, if you look back and you've paid attention, remember when we did the limit definition, we found the derivative and we got stuck. We got 2 to the x times the limit as h goes to 0. What was it? 2 to the h minus 1 over h? Not a, sorry. H. I'm totally guessing. I don't remember. I don't memorize these things. And notice that this was just a number, and we called it some number. I now know what that number is. It's the natural log of the base. There's a reason we didn't know it at that stage. We didn't know logs at that stage. Now I know exactly. So the derivative of an exponential function is the exponential function. But if that base is not e, it's scaled by a factor of the natural log of the base. So it is quite simple in its final form that if I have any base, then it is the same exponential function times the natural log of that base. So the rate of change of these exponential functions are scaled in a way that's linked to the natural log function. It's weird, but it's cool. Now, in this case, I will admit that I do memorize this guy. I do. Because getting there was not that fast. It wasn't like the case of the general log function, where one line, well, in the simple case, one line and I was there at my natural base, and I can go on to the derivative. It was fast to change the base. It really wasn't something I needed to memorize, in my opinion. Whereas this one, there's some steps involved here, right? Yes, you can streamline it a little bit, but you have to rewrite it to the base E version, and that's a little bit more work than the log situation. For the longest time, I actually did this every single time. And it actually helped me in hindsight to really understand what's happening here. But for the sake of efficiency, it's a little bit unnecessary. Because the end result is a very small adjustment of the exponential function that I had originally. Now compare this to the derivative of e to the x. My pen looks weird. Would this formula work? Well, it says e to the x, natural log of e. Where's the natural log of e? Ooh, that was supposed to be a curly bracket. Whoops. Curly. Natural log of e, well, this represents the power of e that would get me the inside of the log, which is e. It's 1. Which I truly, truly hope everyone is super happy with, because we're going to see this many, many times. So I do get e to the x back, even in this general case. The natural exponential function is the only one that is not scaled when I look at its rate of change. All the other guys are scaled by some factor, and that factor is linked to the natural log, weirdly enough. Well, it's not that weird, I guess. Where there's an exponential function, there's a log in the background, and they can always be rewritten as the other one. So, because this doesn't look so bad, I end up just memorizing it. I do. It sort of happens naturally after a while anyway. So it is the same, but if the base is an e, I multiply by, this is just a number. There are no x's in there, natural log of a. Okay. Any questions on that? Of course, it's just like anything else, it just needs practice. We'll do a couple because we have 4 minutes left, but it's up to you. It's up to you. And hopefully you see that if I don't keep up with every class and every discussion, things get out of hand very quickly. If you look back, if you took notes or you take screenshots or whatever, we've done a lot, and it snowballs very, very quickly. You need to stay on top of everything. Let's do a couple basic examples. Let's call it y, let's call it 3 to the x, simplest case, just, whoopsie, that was an eraser too. I see, exponential function, base is not e. The derivative is 3 to the x. But because the base isn't e, I have that number popping out. I just use brackets to make it clear this is a single number being represented. What is that number? Put it in your calculator. Who knows? I don't memorize these things. But it's that simple. It's that simple. Let's try another one. Let's say 5 to the x squared plus 1. I have a secret crush on x squared plus 1. I don't know why. Now, we have 3 minutes. So let me ask you a question. What is the first property I'm going to use for this one? And I don't mean these properties. Technically, this is not a property. This is just how it works. My original list of 7 properties. What is the first property that I'm going to use here? It is the chain rule. You have to see it. You have to see function of a function, which is a little tricky because there are no brackets, right? That doesn't change that it's a function of a function. Make sure you can read this. It's up to you. So I have my outside function, which is 5 to the something. Derivative of 5 to the something, 5 to the something. But because it's not base e, log 5. Oops, that looks like a u, I'm sorry. My ends look like u's. Don't know why. Times, says the chain rule, the derivative of the inside something, 2x. People look at this and say, oh, you multiply 3 things, but the chain rule only has 2 things multiplied. What happened here? This is not the second part of the chain rule. It is part of the first part of the chain rule and the fact that I am working with a general base exponential function. So I feel that this moment in time, this is where things take a step up. When we get to exponential and log functions, now we're asking who is going to keep up with this acceleration in pace and increase in complexity, and who is going to be left behind. Up to this point, it was all pretty basic stuff. And we slowly eased in with some review, a lot of time on polynomials, some behavior issues with limits, and now bam, we add some functions and we go. It is up to you to not be left behind.